Hello everyone. In today's video lecture, we are going to discuss a very important chapter, that is biomolecules. So today's discussion will be based on this biomolecules. So the heading for today's discussion is biomolecules. So let me write down biomolecules. So before proceeding with this discussion on biomolecules, let's define what is the meaning of biomolecules. So as the name suggests, biomolecules, molecules which are important for living beings. Initially, this was supposed to present only in living beings. Now, these molecules can also be synthesized outside the living being. So, based on this, the definition of biomolecule is given as all those molecules which are important for the biological process of the living being. So, under these biomolecules, we have a number of important compounds like carbohydrates, proteins, amino acids, nucleic acids, etc. So we'll take up one by one. So first of all, we'll take up the first important compound, that is carbohydrates. So let's start with these carbohydrates. In many of the books, these carbohydrates are defined as the hydrates of carbon. But now there are many compounds which does not follow this formula, this molecular formula, that is the hydrates of carbon. So now we are going to modify the definition of carbohydrates as these are polyhydroxy aldehydes or ketones or any organic compound which on hydrolysis gives polyhydroxy aldehydes or ketones. So those compounds are collectively known as carbohydrates. So the definition is compounds that is polyhydroxy aldehydes or ketones. So polyhydroxy aldehydes or ketones, that means these organic compounds called carbohydrates contains functional groups, that is alcoholic functional group, and the aldehydic or the ketonic, that is carbonyl functional group. So these are bifunctional organic compounds. So these are known as polyhydroxy aldehydes or ketones, or compounds that on hydrolysis gives these polyhydroxy aldehydes or ketones. So these compounds are collectively known as carbohydrates. So we are having this. So these carbohydrates contains functional groups. So the functional groups present in these carbohydrates, there are two functional groups which is present here. One is OH functional group, the other one is carbonyl functional group. This is the alcoholic or the hydroxyl group. This is the aldehydic or ketonic group. Now if you look at the seniority order of the groups, the priority order of the group, the priority order is assigned to the aldehydic group or the ketonic group. So in this polyhydroxy aldehydes and ketone, this carbonyl group is the principal functional group, whereas this hydroxyl group is secondary functional group. So we have this principal functional group, that is carbonyl group, that is aldehyde or ketone, whereas the secondary functional group is alcoholic group. Now these alcoholic groups may be primary or may be secondary. or we may have both primary as well as secondary alcoholic functional groups present in the organic compound, that is carbohydrates. So simply say these are the compounds which contains aldehyde group or ketonic group along with hydroxyl functional group, where this aldehyde or ketonic group is the principal or the main functional group, and this hydroxyl group is your secondary functional group. Or any compound which on hydrolysis gives rise to this polyhydroxyaldehyde or ketones, these compounds are classified as the carbohydrates. So this is from the definition point of view. Now once we have this definition of the carbohydrates, now the next one is we have to classify these carbohydrates, that is the classification of these carbohydrates. Now these carbohydrates, all sorts of substance or the compounds known as carbohydrate is generally classified or broadly classified into two categories. One is known as sugars, the other one is known as non-sugar. Sugars are also known as saccharides, that is sweet in taste, and the other one is non-sugar. These are known as polysaccharides, and these non-sugars or polysaccharides, these are not sweet in taste. So general or broad classification is sugar and non-sugar. Sugars are sweet in taste and these are known as saccharides, and the other one is known as polysaccharides, which is also known as non-sugar or does not have sweet in taste. Now coming to this sugar, we will further classify this sugar into various forms again. These saccharides, these saccharides is classified into again monosaccharides, and oligosaccharides. So we have the saccharide. Saccharide is further sub-classified into two, monosaccharides and oligosaccharides. Now these monosaccharides, these are the sugars, the smallest unit of the sugar, means which cannot be further hydrolyzed into smaller unit. So those saccharides are known as monosaccharides, means these are the one containing only one sugar unit. So these are known as monosaccharides. Contains only one unit or which cannot be further hydrolyzed into smaller unit. That means this is the smallest unit. The smallest unit of carbohydrate or the sugar is known as monosaccharide. This being the smallest unit, these cannot be further hydrolyzed into smaller units. So example of this monosaccharides, we have glucose, we have fructose, we have galactose, glucose, etc. So these are known as monosaccharides. On the other hand, look at this oligosaccharides. These are the sugars which contains 2 to 10 saccharide units, monosaccharide units. Contains 2 to 10 monosaccharide units. So those carbohydrates containing 2 to 10 monosaccharide units are known as oligosaccharides. That means these oligosaccharides on hydrolysis will give you 2 to 10 monosaccharide units. Those are known as oligosaccharides. So if the number of saccharide is 2, we say this is disaccharide. An example of disaccharide is we have maltose, we have sucrose, we have lactose, etc. If the number of saccharide unit is 3, we have tri. If the number of saccharide unit is 10, we have deca. If the number of saccharide unit is 5, we say this is pentasaccharide. So this is how this saccharide is subclassified. So saccharides into monosaccharides. Mono is the smallest unit of the sugar which cannot be further hydrolyzed. Whereas the oligosaccharides contains 2 to 10 monosaccharide units. That means these on hydrolysis will give you 2 to 10 small monosaccharide units. And the most important of all these saccharides, we have these disaccharides. In this disaccharides, we have maltose, sucrose, lactose, etc. So this is how we classify saccharides. Now these monosaccharides is further subclassified into various forms. So we have these monosaccharides. These monosaccharides can be classified into aldose or ketose. Those monosaccharides are known as aldose if the principal functional group is aldehyde group. If the principal functional group is ketonic group, those monosaccharides are known as ketose. So aldehyde principal functional group is aldehyde. So if means along with this hydroxyl group, we have this aldehyde group as a principal functional group. So example of this aldose is we have this glucose. Glucose is an example of aldose. On the other hand, those monosaccharides in which the principal functional group is ketone is known as ketose. Here the principal functional group is ketone. And the best example of this ketose is fructose. So fructose is a ketose, whereas glucose, galactose, mannose, these are aldose. So these monosaccharides based on the functional group, this is based on the principal functional group, is classified as aldose or ketose. If the principal functional group is ketone, we say ketose. If the principal functional group is aldehyde group, then we say this is aldose. Now whether we have this ketose or aldose, these ketose or aldose can be further subclassified into that is, this is based on the functional group. Now the second classification is based on the number of carbon atoms. Based on number of carbon atoms present in the monosaccharide unit. Whether we have this aldose or ketose, these aldose or ketose can be classified further into the number of carbon atoms present. So based on the number of carbon atoms present, this can be classified as triose. So triose means those monosaccharides containing 3 carbon atoms. So the smallest value of the number of carbon atoms that can be present in a carbohydrate is 3. So smallest unit of carbohydrate contains 3 carbon atoms. So triose means 3 carbon atoms. So we have 3 carbon atoms. If the number of carbon is 4, we say this is tetrose. 4 carbon atom. If the number of carbon atom is 5, we say this pentose. We have 5 carbon atoms. If the number of carbon atoms in the monosaccharide unit is 6, we say this is hexose. So this classification of monosaccharide, this is based on the number of carbon atoms present in the monosaccharide unit. So the first one, that is aldose ketone, this is based on the principal functional group. Now these carbohydrates can also be classified based on whether this reduces Tollens reagent, Benedict solution or the Fehling solution. So next classification of this is reducing and non-reducing. Reducing sugar and non-reducing sugar. So this classification of saccharides into reducing and non-reducing, this is based on their chemical reactivity with Tollens reagent, Benedict solution or the Fehling solution. These reducing sugar, so a class of sugar is known as reducing when if this reduces Tollens reagent, reduces Fehling solution or Benedict solution. So if the given sugar solution reduces Tollens reagent, Fehling solution or Benedict solution, those sugars are known as reducing sugar. So whenever we have this reducing sugar, all these reducing sugar, either they have free aldehyde group or free alpha hydroxy ketone group. Alpha hydroxy aldehyde or ketone group. So those carbohydrates containing alpha hydroxy aldehyde or ketone groups will show reducing property, and those sugars are known as reducing sugar. So either they have alpha hydroxy aldehyde or ketone group, or they are in hemiacetal or ketal form, hemiacetal or hemiketal form, or they are in open chain structure. Means either they have free aldehyde group or free alpha hydroxy ketone group, or that they have alpha hydroxy aldehyde or ketonic group, or if they are in hemiacetal or hemiketal form, that form will reduce this Tollens reagent, Fehling solution or Benedict solution, and those sugars are known as reducing sugar. So this is based on chemical property with this Tollens reagent, Fehling or Benedict solution. So the best example of this reducing sugar is we have glucose, we have fructose, we have lactose, we have maltose. So these are known as reducing sugar. But if the sugar does not reduce any of this reducing agent, then that sugar is known as non-reducing. So this does not reduce Tollens reagent, Fehling solution or Benedict solution. So if the sugar solution does not reduce these reagents, those sugars are known as non-reducing sugar. So non-reducing sugar does not have any of this groups. They exist in acetal or ketal form. This was in hemiacetal or hemiketal form. But if the sugar exists in acetal form or ketal form, means there is no free aldehyde or free ketonic group, or there is no alpha hydroxy aldehyde group or alpha hydroxy ketonic group, then those sugars will not reduce Tollens reagent, Fehling solution or Benedict solution, and those sugars are classified as non-reducing sugar. And the best example of this non-reducing sugar is sucrose. So sucrose is a disaccharide which is non-reducing, whereas all these disaccharides and monosaccharides, these are all reducing sugar except this sucrose. So this, look at this, we have lactose, maltose, these are disaccharides, but they exist in hemiacetal form or hemiketal form, or either they are having free aldehyde group or alpha hydroxy ketone group. So they reduces these regions and these are known as reducing sugar. So this is one of the classification based on their reactivity towards all these reagents. So these are the brief classification of the carbohydrates. On the other hand, now look at this, we have polysaccharides. So as we have seen polysaccharides, that means those carbohydrates containing more than 10 monosaccharide units, those are known as polysaccharide. And the best example is we have starch. Starch is the best example of this polysaccharides. So starch, cellulose, etc. These are known as polysaccharides. So polysaccharide is those having more than 10 saccharide units. These are known as polysaccharides. Now next, after this classification of carbohydrates, next we comes to the stereochemistry of the carbohydrates. Now whether we have triose, tetrose, pentose, hexose, we have to specify the stereochemistry of these carbohydrates. Now the stereochemistry of this carbohydrate says all carbohydrates are optically active, So I'm saying all carbohydrates are optically active. That means either these are dextrose form or ribose form. So this dextrose or ribose, this can only be identified when we put this solution in polarimeter. So just by looking at the molecule, we cannot say whether this will undergo clockwise rotation, that is dextrose form, or whether this will rotate the plane of plane polarized light in anti-clockwise direction, that is liborotated. We can simply identify whether this molecule will rotate the plane polarized light. That is what we call as optical property. So all carbohydrates are optically active and have D configuration. So now look at this capital D has nothing to do with small d and small l. Small d and small l, this represents the optical property, that is the dextrose form or the ribose form. That means whether that particular molecular solution will rotate the plane of the plane polarized light into clockwise direction or anti-clockwise direction. That is small d and small l. Now where I am saying all this carbohydrate has called capital D configuration. So this capital D configuration, this is nothing but the relative configuration. This is relative configuration. So once we have this is relative configuration, so there must be some standard reference to measure the configuration of this carbohydrate. So this being a relative configuration, the standard reference to use करेंगे, the standard reference used is glyceraldehyde. So the glyceraldehyde. So the relative configuration of all carbohydrates can be related to this glyceraldehyde, the configuration of glyceraldehyde. Once we know the configuration of glyceraldehyde, we can relate the configuration, that is not the absolute but the relative configuration of the carbohydrates. So this D configuration, this is defined by a formula known as Fischer formula. So Fischer relative configuration. So Fischer was the scientist who gave this relative configuration. Now we are saying that the reference compound used to determine the configuration of carbohydrate is glyceraldehyde. So we have this glyceraldehyde. The compound glyceraldehyde is CHO, CHOH, CH2OH. So we have this three carbon containing compound. This is aldehyde group. We have carbon, hydrogen, OH. So this carbon is chiral, whereas first carbon and the third carbon is achiral. So based on the configuration of this, we'll define the configuration of the carbohydrate. Now this being a chiral, ये आपके पास chiral है, so this can exist in two enantiomeric forms. So we say look at this CHO Then we have this is CH2OH. We have this hydrogen. This is the chiral compound, and we have placed OH on the right hand side. This is one of the possible configuration. The other possibility is we have, look at this, CHO, CH2O. We have this OH, and this is hydrogen. So these are the two possible configurations for this compound glyceraldehyde. This is the compound glyceraldehyde. Now we have one chiral center, so the placement of groups in this chiral center can be on this way. Now what if you place a mirror? If we place a mirror here, then these two are the mirror images of each other. So these compounds containing one chiral center, which are mirror images of each other, these are what we call as enantiomeric pair. So enantiomers are those optically active isomers having non-superimposable object and its mirror image relationship. So we have an enantiomeric pair. So in this first, the OH group is on the right hand side. Look at this. In this particular configuration, at the chiral center, the OH group is on the right hand side. So these isomer in which the OH group is on the right hand side is arbitrarily assigned as the capital D form. So this capital D has something to do with this, the placement of OH. If the OH is on the right hand side of this glyceraldehyde molecule, then this isomer is known as D form. On the other hand, its mirror image in which the OH is placed on the left hand side. So in this particular form, OH is on left hand side. So this particular isomer in which the OH is placed on left hand side, this isomer is known as L isomer. So this capital D and capital L is nothing but the placement of OH group at this chiral center. If the OH group is on the right hand side, that isomer is known as capital D isomer. If the OH is on the left hand side, this is known as the capital L. So these D and L are mirror images of each other, that is enantiomeric pair. Now we can construct all carbohydrates from this glyceraldehyde. We can increase the number of carbon atoms by chemical reaction. So if we increase the number of chiral centers, then in all these carbohydrates, this configuration will remain as it is. So this configuration CHOH and CH2OH, this group is present in all the carbohydrates. So now we are going to check the configuration of those carbohydrates with the configuration of this glyceraldehyde. So this particular group, the one which is placed in red color, this group is common to all carbohydrates. Common to all carbohydrates. So this being common to all carbohydrates, so we'll compare the configuration of those carbohydrates with the non-configuration of this glyceraldehyde. So irrespective of the chiral centers present in all the carbohydrates, we are least bothered about the other chiral centers. We are just bothering about the configuration at the highest chiral center. If the configuration of those carbohydrates at the highest chiral center is on the right hand side, then that isomer is known as capital D isomer. If the configuration of OH at the highest chiral center is on the left hand side, then this is known as the L isomer. So this is simply based on the configuration of this chiral center. So by definition, a particular carbohydrate is known as D isomer if the OH group at the highest chiral center, is at right hand side. So if the OH is on the right hand side, this is known as D isomer. L isomer, if the OH at the highest chiral center is at left hand side. So this is how we develop the relative configuration, that is D and L, capital D and capital L configuration. So let me explain this by use of this example of glucose and fructose. So we take the example of glucose. The molecular formula of glucose is C6H12O6. Now the chemical formula, look at this. This is CHO, CHOH. We have 4 CHOH 4 units, then we have CH2OH. So we have, look at it, this carbon which is placed in the first bracket, all these 4 carbons are chiral. So we have 4 chiral centers here. So now look at this. This is CHO, CH2OH. In between this we have 4 carbon atoms. We have OH on the right hand side, hydrogen, OH left side, hydrogen, OH, H, H, OH. So this is the first carbon. So 1, 2, 3, 4, 5, 6. So look at this. This is the highest chiral center. In this highest chiral center, we have this, the configuration of the glyceraldehyde. So look at this. In this highest chiral center, the OH is on the right hand side. So we say this is D-glucose. So if I say D-glucose, means the OH on the highest chiral center is on the right hand side, as that we have seen in case of glyceraldehyde. So we are focusing on the chiral center at the highest chiral center, irrespective of the configuration at the other carbon atom. So this D and L, capital D and capital L configuration, focus only on the highest chiral center, irrespective of the other chiral center. We are least bothered about this rest of the chiral centers. We are just focusing on this highest chiral center. Now take any other form. If we place a mirror image, mirror here, take its mirror image, then we have this CHO, CH2OH. Now this weight will be on left hand side. So this is a mirror image. Now this is glucose, D-glucose. Now look at this. The position of OH at the highest chiral center, this is the highest chiral center. The position of OH at the highest chiral center is on left hand side. So if OH is on left hand side, we say this is L isomer. So this is the L isomer. So all naturally occurring glucose are capital D form. So this is D-glucose. D-glucose is also known as dextrose form, because all these are optically active. As I have told you, these are optically active. So this glucose, which is written as capital D. So capital D means the configuration at the highest chiral center, which is on the right hand side. So all naturally occurring carbohydrates are capital D form. This glucose is also known as dextrose, meaning thereby this being an optically active compound, this rotates the plane of the plane polarized light in clockwise direction. So these are known as dextrose form. So this is what we call as the relative configuration of the carbohydrates. This is based on the Fischer projection formula, and the reference compound used for this relative configuration is glyceraldehyde. Now in this glucose molecule we have 4 chiral centers, whereas in this glyceraldehyde we have only 1 chiral center. So while discussing this relative configuration, focus only on the highest chiral center configuration or the relative position of the OH in the highest chiral center. If the OH is on right hand side or left hand side, if this is on right hand side, we say this is D form. If this is on left hand side, we say this is L isomer. Now after this configuration, the relative configuration of carbohydrates, now we come to the Haworth structure, that is cyclic structure or ring structure of carbohydrates. Many of these carbohydrates in combined state, they exist in ring or cyclic structure. So to explain the presence of ring or cyclic structure, we take the help of Haworth structure. So this Haworth structure represents the cyclic or the ring structure of carbohydrates. So we'll take this example of glucose. So we'll start with glucose. So we have this, first we'll take up this glucose. So this is CHO, that is C double bond O H, that is aldehyde group. We have this CH2OH, OH, H, we have OH, we have OH, H, H, OH, H. This is the open chain structure of D-glucose. So we say this is D-glucose open chain structure. Why this is known as D? Because at the highest chiral center OH is on the right hand side, so we say this is D, capital D form. Now this open chain structure, ये open chain है. So this open chain structure can be converted into a cyclic structure. Now let's see how this undergoes cyclization to give you the cyclic structure. Now in the same molecule, that is D-glucose, we have aldehyde group and we have alcoholic group. Alcohols react with aldehydes and ketones to form acetals or ketones. So this is the reaction between the OH present in glucose with the principal functional group, that is aldehyde group. Now the OH present in the fifth carbon atom, that is the highest chiral center, these OH, oxygen lone pair electron, this electron attacks this electrophilic carbon and this pi electron is shifted to oxygen. That means when this electron pair from oxygen attacks this electrophilic carbon, pi electron is shifted to oxygen, so oxygen equals negative. To this negatively charged oxygen, this H plus ion goes here. So in this way, a 6-member cyclic structure is formed. So look at this, 1, 2, 3, 4, 5, 6. So glucose exists in 6-member cyclic structure. So there are two possibilities. Now this carbon is sp2 hybridized. So look at this, we have a planarity. This carbon, aldehyde carbon is sp2. So this is a planar. So OH can attack from this side or from this side. Now based on this, we have two possibilities here. So take this CH2OH, we say this is OH, this is hydrogen. Now we have this CO, so this is carbon oxygen bond. Then we have rest, this is OH, H, OH, H, this is OH, H. The other possibilities is hydrogen on left side, OH on right hand side. The rest as it is, we have OH, H, OH, H, OH, H. So these are two possibilities. So these two possibilities arise only because of this aldehyde carbon being sp2 hybridized planar. So there are two possible ways of this, the newly developed chiral center. So initially look at this, open chain contains only 4 chiral center, 1, 2, 3, 4. Now when they cyclize an additional new chiral center, so इस particular molecule में देखिए this D-glucose open chain 4 chiral centers. Now this is cyclized form. This cyclic structure contains 5 chiral centers. इसमें आपके पास 4 chiral center है. Now this is converted into 5 chiral center. Now this newly developed chiral center, देखिए this is the newly developed chiral center. Except this newly developed chiral center, all the configuration in the rest of the chiral centers are exactly identical. So this newly developed chiral center, this carbon number 1, this is known as anomeric carbon. So anomeric carbon is that carbon in which the configuration at carbon number 1 differs. So this newly developed chiral on cyclization is known as anomeric carbon. So we have this anomeric carbon. Now these two isomers in which the configuration at the anomeric carbon difference, these two isomers are known as anomers. So anomers are isomers which differs in the configuration of anomeric carbon. Look at this. In the rest of the chiral center, configuration is exactly identical, but only difference in the anomeric carbon. So these two isomers are known as anomers. This can be written as in this way: CH2OH OH 1, 2, 3, 4. We have OH, H, OH, H, OH, H, which is on right hand side. So we have this. This can be written as in this way: CH2OH OH, H, OH, H, OH, H, OH, H. This is now this. Look at it. This can be converted into this cyclic form, 6-member cyclic form, starting with this carbon. So now look at this. We are starting from this. This carbon is anomeric carbon. So now groups on the right hand side of this Fisher projection formula, they are written below the plane of ring, and those on the right hand side, they are left hand side, they are written above the plane of ring. Now this CH2OH, this is always written above the plane of ring. So we have, look at this, CH2OH, this is CH2OH. Now this carbon is anomeric carbon. At this anomeric carbon, if the OH on this anomeric carbon, this is anomeric carbon, if the OH is on left hand side, this is written above the plane, and this OH is on right hand side, so this is written below the plane of ring. The rest, look at this, we have, this is OH, 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 H, 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 H. This is H, we have H here, OH, H, OH, H, OH, H, H. Now these two forms, if the OH is above the plane of ring, this OH is above the plane of ring, we say this is beta D glucopyranose ring. If the OH and the anomeric carbon is below the plane of ring, you say this is alpha D glucopyranose ring. And this glucose, the cyclic structure of glucose exists in two isomeric form. One is known as beta D-glucopyranose, the other one is known as alpha D. Beta, in which the OH is above the plane of the ring, alpha, in which the OH at the anomeric carbon is below the plane of ring. So these two isomers, alpha form and beta form, which are nothing but the anomers, because the difference in the chiral center or configuration of the anomeric carbon, these two forms are nothing but the hemiacetal form. So these are hemiacetal form. So the cyclic structure of glucose, that is alpha form and beta form, these are nothing but the hemiacetals, and these hemiacetals alpha and beta form, these are known as anomers. The reason being, these two isomers differs in the configuration of the first chiral center, that is the newly developed chiral center, which is known as anomeric carbon. In the rest of the molecule, the chiral center remains as it is. This 6-member ring, this is also 6-member ring, this is also 6-member numbering. Okay, this is carbon number 1, carbon number 2, 3, 4, 5, 6. This is chiral carbon or anomeric carbon. 2, 3, 4, 5, 6. So this 6-member cyclic structure. So glucose exists in 6-member cyclic structure. This 6-member cyclic structure, hemiacetal form, this is known as pyranose ring. Pyranose ring. So glucose, D-glucose exists in 6-member pyranose ring. One is known as alpha D-glucopyranose, in which the OH at the anomeric carbon is below the plane of ring, and the other one is known as beta D-glucopyranose, in which the OH at the anomeric carbon is above the plane of ring. So this is what we call is the Haworth structure of glucose. So glucose, in most of the carbohydrates, many of the properties of glucose cannot be explained by use of this simple open chain structure. Those properties which cannot be explained by using this open chain structure can be easily explained by this cyclic structure. So means in many of these compounds of glucose in combined state, they exist in this cyclic structure, and these two cyclic structure, alpha form and beta form, these are interconvertible, and both these alpha form and beta form, these are optically active isomer. In aqueous solution, this alpha form and beta form exist in equilibrium. So suppose we have this aqueous solution. In aqueous solution, this alpha form is in equilibrium with open chain structure, which is in equilibrium with beta form. That means alpha can be converted into beta and beta can be converted into alpha, means both are in equilibrium, and this equilibrium is through open chain structure. That is, in this equilibrium, alpha exists in 36%, beta exists in 64%. So the measured quantity of this glucose exists in beta form, and this open chain is almost 0.02%. So this is the percentage composition of alpha and beta and open chain. That means alpha and beta are interconvertible. So this interconversion from alpha to beta is through open chain structure. So this is equilibrium proportion. Now all these are optically active. So specific rotation of this alpha form, that is 110 degree, that is plus, that is dextrose form. The specific rotation of this beta form, that is plus 19.7 degree, and the freshly prepared alpha D-glucopyranoside solution on standing changes to an equilibrium value, a constant value, and that constant value is for this open chain, and this is 52.7 degree. That means if we are starting with this alpha D-glucopyranose, this freshly prepared alpha D form on standing, this specific rotation decreases from 110 to 52.7 and this remains as it is. On the other side, if we are starting with freshly prepared beta D glucopyranose solution, this on standing changes to a constant value. That is, initially this was having 19.7 specific rotation. Now this increases and changes to this 52.7. Now this change in optical rotation from 110 to 52.7, that is equilibrium value, constant value, or from 19.7 degree to 50.7. Change in optical rotation of this alpha form or beta form in aqueous solution to a constant value is known as mutarotation. Mutarotation, change in optical rotation. So both alpha form and beta form on standing in solution changes to a constant value of 52.7. This increase or decrease in optical rotation of alpha and beta form on standing to a constant value of 52.7 is known as mutarotation. So all this alpha form, beta form and open chain form, these are all dextrose. So open chain, which is almost 0.02%, optical rotation of this open chain is 52.7, that is the equilibrium mixture. So equilibrium mixture of alpha and beta changes from the alpha decreases from 110 to 52.7, whereas beta form increases from 19.7 to 52.7. So there is decrease in optical rotation from alpha and there is increase in optical rotation from beta. So this change in optical rotation is what we call as mutarotation. Similar to the cyclic structure of glucose, fructose also exists in cyclic structure. So now we are going to discuss the cyclic structure or the ring structure of fructose. So fructose, this fructose is also the fructose because at the highest chiral center the OH is on the right hand side. Open chain structure is, we have CH2OH, C double bond O, CH2OH, we have OH, OH, H, OH, H, H. This is D-fructose. At the highest chiral center, OH is on right hand side. Now, this fructose exists in 5-member cyclic state. Now, what is happening is, in the same molecule, we have oxygen containing 2 lone pair. We also have a ketonic group. So, this reacts to give you hemiketal form. Now, when this reacts, look at this, similar to cyclization of glucose, this sp2 hybridized carbon being planar, this O can attack from either side, giving rise to 2 cyclic structure. So one of the possibilities is we have OH, CH2OH, CH2OH, OH, OH, H, OH, H, H. This is one structure. The other possibilities is CH2OH, we have OH on left side, CH2OH, H, OH, H, H. So these are 2 possible. Again, look at it. This newly developed chiral center. This is the newly developed chiral center. So before this open chain, we have 3 chiral center. But once we cyclize, a newly chiral center is developed. So this contains 4 chiral centers. So this newly developed chiral center, this is what we call as anomeric carbon. Anomeric carbon. So these 2 isomers, in which there is a difference in the configuration of the anomeric carbon, these 2 isomers are known as anomers. So glucose, similar to glucose, fructose also exists in 2 anomeric forms. The newly developed chiral center is known as anomeric carbon, and it is this carbon in which the configuration is different. So this can be written as CH2OH. So we have O, CO bond, H, OH, H, H, OH. Now OH is on right hand side, so we place it here. This is OHCH2. The other one is CH2OH. OH on left hand side. So this can be written as, we say this is a 5-member cyclic structure. This 5-member cyclic structure of fructose is known as Furanose ring. This is the anomeric carbon. Now at this anomeric carbon, this is anomeric carbon. Look at this, OH is on right hand side. So if OH is on right hand side, we have to place this OH below the plane of ring. So we have this CH2OH. This is carbon number 1, 2, 3, 4, 5, and the 6th carbon CH2OH. This is always placed above the plane of a ring. So OH below the plane of ring. Then we have hydrogen, OH, OH, hydrogen, hydrogen. Similar, look at this. CH2 is above the plane. Now CH2 will be below the plane. Raise as it is. H, OH, OH, H, H, CH2, OH. 4, 5. This is 6th carbon. Now, in one of these structures, the OH at the anomeric carbon is below the plane. So OH below the plane, this is known as alpha D fructofuranose. If the OH at the highest anomeric carbon is above the plane of ring, then we say this is beta D fructofuranose. These two isomers, that is, these two are anomers. These two anomers are coming from ketone. This is ketose. So these are hemiketal form. So the 5-member cyclic structure of fructose exists in hemiketal form, and this hemiketal form, 5-member, this is known as Furanose ring. Furanose ring. So in both the case, look at this alpha form and beta form. In both this alpha form and beta form, the only difference is the stereochemistry at the anomeric carbon. The rest of the stereochemistry remains as it is. So many of the properties of fructose can be explained by use of this cyclic structure. In many of the compounds, carbohydrates containing fructose as a monosaccharide unit contains this cyclic structure. So this is how cyclic structure came into being. That is, for glucose and fructose, we can show this cyclic structure. Glucose being aldehyde, the cyclic structure is 6-member hemiacetal form, which is known as Furanose ring. The 5-member ring coming from this fructose is known as hemiketal form, and the 5-member ring is oxygen containing ring is known as Furanose. So this is alpha and beta form. So this alpha and beta form shows the presence of the cyclic structure of the glucose as well as fructose. So this is what we call as the ring structure or the Haworth structure of carbohydrates.